Okay, 28. Part A. Look, Part A should be less difficult for you than Part B. Part B requires a realization, which I'll go over here. Now look, Part A. So this roller coaster car goes down this hill, and we're focusing on the car. So I'm going to kind of redraw this hill here. So look, the car goes down like this, and we're focusing on the roller coaster car right there, and we're told that it has a velocity of 20 meters per second at that point. Right at the bottom of that first hill, it's moving at 20 meters per second, and we're being asked to find the force of the track on the vehicle. What do we call the force of the track on the vehicle? Oh, I know. It's called the normal force. The force of a surface holding an object up, the force of a surface holding an object up is called the normal force. So the forces on this car, we have mg down, and we have normal force up. That's our free body diagram. Where's the center of the circular path here? Is the center of the circular path down here or up here? Up. It's up. The center of the circular path, this dot, let's say this dot right here represents the center. Okay? Now, why is the center of the circular path important? Because the center of the circular path is always going to be positive, because that's where the acceleration points. Okay, so we sum the forces. We sum the forces on the car. We have normal force up, mg down, center of the circle is positive. Sum of the forces always equals ma, but this A is special. It's a special A because notice that the car is in a circular path. Whenever an object's in a circular path, we have what's called a centripetal acceleration. So this is a centripetal there, right? What's the equation for centripetal acceleration? It's v squared over r. Okay, so we're going to plug that in. So now we can solve for the normal force, which is what they want. So this is going to be m v squared over r plus mg. So the radius, is that angle? Hold on. All right, so where were we here? So r, what's the radius of this first circular path? The radius is 10. So guys, you plug the numbers in. We got the mass is 500. That gets plugged in for m. The velocity is 20. So when you plug in, you get 24,900 newtons. That's the normal force on the car. Okay? Now, part B, let me revert this. Everybody got that copied? Part B, we're focusing up here at the top of the hill. Now, the realization that you must have, so everybody pay attention to this. So I want you to imagine that we send the car over this hill 5 times, okay? And every time, hold on, everybody's calling me today. All right, part B, we're focusing at the top of the hill. I want you to imagine, we send the car over the hill 5 times. And every time we send it over the hill, it's going to go faster. So the car goes like this. It goes over the hill once. Then it goes again, but faster. Over the hill again, but faster. And then again, faster and faster. Guys, if we kept sending the car over the hill faster and faster and faster and faster and faster, eventually we're going to reach a velocity where the car does what? Flies off, where it catches air. Now, so in other words, the car leaves the track. There's going to be a velocity where the car starts to leave the track. Now, let's look at the free body diagram. What forces are on the car? Well, we got mg down, and we got normal force up. Does that make sense?
Yes.
Remember, center of the circle is always plus. So when you sum the forces here, you're going to go like this. You're going to go mg minus normal force. Why is the normal force minus?
Because it's not pointing toward the center of the...
It points away from the center, right?
It's not pointing toward that.
Sum of the forces equals ma. Now this A is a centripetal because the car is in a circular path, right? Whenever an object's in a circular path, it has a centripetal acceleration. The insight to this problem has to do with the normal force. Because look, what we're going to do is we're going to plug in centripetal acceleration. It's v squared over r. We plug that in down there. So now what we have is mg minus the normal force equals mv squared over r. The normal force, when the car leaves the track, right? What happens to normal force? It goes to 0. Or if that confuses you, what you could do is you could set it equal to 0.000000001. So in other words, the normal force is barely there, but basically it's 0. So now what we're left with is mg equals mv squared over r. The m's cancel, and you get v equals square root gr. So g is 9.8. The r is 15. That's a meter per second squared. So this comes out as 12.1 meter per second. And that's the velocity. Look, if you plug that velocity in right there, the normal force will be 0. It's the velocity where the car starts to leave the track.